NCCL, NVIDIA Collective Communications Library, high-performance GPU to GPU communication primitives for efficient distributed deep learning and parallel computing. NCCL enables low latency and high bandwidth communication across multiple GPUs and nodes. Example, tensor parallelism. Large models are split across multiple GPUs, requiring efficient communication between them. Communication channels. NCCL subdivides every collective into parallel communication channels. Each channel runs on a separate streaming multiprocessor, enabling fine-grained parallelism. This maximizes GPU utilization and link bandwidth, especially for large payloads. Communication protocols. NCCL uses 3 protocols optimized for different message sizes and performance goals. Simple protocol, designed for high bandwidth with large messages, uses memory fences for synchronization, achieving near-peak bandwidth but with higher latency around 6 microseconds per hop. LL protocol, low-latency protocol optimized for small messages, uses lightweight flag-based synchronization instead of memory fences, achieving around 1 microsecond latency but only 25 to 50% of peak bandwidth. L128 protocol, the best of both worlds, combining low latency with high bandwidth, transmits 128 byte units with flag-based sync, achieving around 95% of peak bandwidth and 2 microsecond latency, ideal for a broad range of message sizes. Data transfer methods. NCCL employs distinct strategies for intra-node and inter-node communication. Intra-node communication uses GPUDirect peer-to-peer technology. GPUs communicate directly over NVLink or PCIe without staging through CPU memory, providing the lowest latency and highest bandwidth path. Inter-node communication uses network interface cards with RDMA capabilities. For high-performance networks like InfiniBand, GPUDirect RDMA enables the NIC to access GPU memory directly, bypassing the CPU entirely. Communication primitives. NCCL builds high-level collectives from low-level primitives that encapsulate basic data movement patterns. ReduceSend receives data from a peer, performs element-wise reduction with local data, and sends the result forward. This is the core primitive for reduction operations. recvCopySend receives data, copies it to the output buffer, and forwards it unchanged, used in broadcast and AllGather operations. RecvReduceCopySend combines recvReduceCopy to output and send. This primitive completes reductions and prepares results for distribution. AllReduce uses a ring topology where each GPU communicates with its immediate neighbors. The operation combines a distributed reduction phase with a data dissemination phase. All GPUs now have the same reduced result, which is the sum of all matrices. AllReduce is bandwidth optimal and excels for large messages. AllReduce uses a tree topology with a root, middle, and leaf nodes. The operation proceeds in 2 phases, reduce upward to the root, then broadcast downward. Phase 1, reduce, leaf nodes send data upward, middle nodes reduce and forward, and the root completes the reduction. Phase 2, broadcast, the root sends the fully reduced result downward and middle nodes forward it to leaves. AllReduce is latency optimal and excels for small messages. AllGather, each GPU gathers data from all GPUs using a ring topology, concatenating them together in order. All GPUs now have the complete concatenated data from all GPUs. Ring broadcast, the root GPU broadcasts its data to all other GPUs using a ring topology, forming a directed chain from root to the last GPU. All GPUs now have the same data from the root GPU. ReduceScatter. This combines reduce and scatter, reduce all data, then scatter different chunks to each GPU. Phase 1, all GPUs reduce or sum their data together as it moves around the ring. Phase 2, scatter different chunks to each GPU. Each GPU receives its designated segment of the reduced result. Each GPU now has a different chunk of the reduced result. ReduceSend performs element-wise reduction across all GPUs, aggregating the final result onto a user-defined root GPU using a ring topology. Only the root GPU receives the fully reduced result. This is useful when only one GPU needs the aggregated data. Summary: we learned about nickel core concepts including communication channels, protocols, and data transfer methods. We explored communication primitives like recvReduceSend, recvCopySend, and recvReduceCopySend. Finally, we covered collective operations including ring AllReduce, tree AllReduce, AllGather, broadcast ReduceScatter, and ring-reduce. Nickel provides high-performance primitives and collectives optimized for both latency and bandwidth across various message sizes, enabling efficient multi-GPU communication for distributed deep learning workloads including training and inferencing.